Can I just read the video?
Yes. So we have Dr. Justin Vetch with us today. He is our new-ish superintendent at the Western Triangle Research Center. We're really glad that we have another superintendent here. It's a really important research center. So he will be speaking to us on pre-harvest sprouting, etc. So we'll turn it over to Justin.
Thanks,
Take it away.
Appreciate it. Thanks for coming, everybody. Guess WebEx can see that all right. So like Adrian said, I'm going to talk to you today a bit about pre-harvest sprouting. Pre-harvest sprouting in northern Great Plains, small grains, mostly just winter wheat, spring wheat, and barley. I'm also going to spend a little bit of time towards the end talking about me coming into the Western Triangle Research Station, kind of the state of the station, plans for the future, etc. We have a lot of things happening right now that I want to make sure that the community knows what's going on. So without further ado, I guess maybe if everything works out here. All right, so today I'm just going to talk a little bit about pre-harvest sprouting. What is it? Why do we care? A lot of my work on pre-harvest sprouting regarded the genetics behind it. And so I'm going to talk to you a little bit about the QTLs and genes of interest underlying pre-harvest sprout. And we care about that because that really helps us breed, resistant varieties. And it's not always a problem, but, 1 in 5 or 1 in 10 years, pretty much every area across Montana gets hammered by it and you lose quite a substantial crop over it. I'll talk to you a little bit about kind of what I've tested so far materials-wise, the different varieties and whatnot, and the methods we use to test those varieties. And then I'll give you some results, of common varieties that you would all know and how they have stood up in our pre-harvest sprout tests. So what is pre-harvest sprouting? Well, it's basically a good picture of it right here. That's what you might see in the field in an extreme case. And pre-harvest sprout is the germination or release of the dormancy of kernels that occurs following physiological maturity. We'll talk a little bit later about what physiological maturity is. That's basically the point at which the plant is capable of sprouting, regardless of its state of dormancy. So sprouting results in a pretty large reduction in usable grain yield, and it really affects the end-use quality, as I'm sure many of you who have been affected by pre-harvest sprout are aware, because it results directly in dockage of the elevator. It's responsible for more than $1 billion in losses per year right now across the Northern Hemisphere, really. It can threaten food and beer security, as wheat provides more than 20% of the global food calories, and everyone knows the best beer comes from barley. So here we have examples of what bread made with different quality of grain might look like. So here you have sound grain, beautiful loaves of bread. Then you get into the sprouted and severely sprouted, and it quickly deteriorates into this doughy, sticky mess that never quite rises and becomes a normal loaf of bread. And then here you can see the differences in kernel structure between sound and damaged grains. Basically here you can see roots starting to sprout. You get enlarged grains and they become really wrinkly. So it becomes pretty obvious to the naked eye when much sprout damage has occurred. So there's quite a few factors that affect pre-harvest sprouting. Some of the primary ones are plant breeding and domestication. And basically there was selection for reduced dormancy by early farmers and even plant breeders today, right? Because say you're planting a crop of spring wheat, you harvest it, you want to turn around and plant it again relatively quickly. Or in the case of like malt barley, you want to harvest it, have a little bit of dormancy when you harvest. So if you get some rain, nothing happens to it. But then the malt house wants no dormancy right away to be able to take that. And so there's been this selection for reduced dormancy, which actually really affects the producer, right? Because if you have no dormancy, you can easily lose your crop to the environment. The other effects are environmental. What causes pre-harvest sprouting is really the moisture during late maturity stages and the high temps during grain filling. And then the things that I've studied the most are the genetic components, such as the spike morphology, hormone sensitivity, and actually what I've studied the most is seed dormancy. And so spike morphology affects pre-harvest sprouting in ways such as awns. varieties with awns, absorb up to 30% more water than an awnless variety. And this can increase sprouting by up to 40 or 50%. And then club wheat varieties, which aren't really that common around here, but those can increase your absorption by quite a bit as well and affect the pre-harvest sprouting. Hormone sensitivity is a really big one, and it's a major focus of research right now because the hormones, particularly abscisic acid and gibberellic acid, really control dormancy and germination. And it's the interplay of those two hormones that really decides things. So ABA, or abscisic acid, hinders germination, basically aids dormancy, while GA, or gibberellic acid, stimulates germination. And here, basically, the important thing to take away from this is the different varieties have different susceptibilities to these hormones, and that the hormones do have a definite effect. So on the x-axis, we have ABA concentration, and on the y-axis, we have rate of germination. So this is just a germination test. And as you can see, if you have no ABA concentration between these two varieties, the circles and the triangles, you get different amounts of germination because there's different amounts of dormancy present. But as you move up in concentration of ABA, you eventually reach a point where you can't germinate the seeds at all because they're responding to that hormone. And so seed dormancy is pretty much the most important factor that we've decided to investigate. It's a really complex quantitative trait, means it's controlled by a lot of different genes. It's really difficult to achieve a perfect level of dormancy, like I was talking about. You know, producers would really like dormancy at harvest, and users would really like no dormancy to be able to turn around and use that grain much more quickly. After ripening also really affects this whole process, because that's kind of the natural process of breaking the dormancy, and that happens different in different varieties as well. And so many, if not most, of the genes being explored for pre-harvest sprout resistance are basically directly related to dormancy. So after ripening is when you harvest your grain. If it's really dormant, you store it for a couple months, and then it breaks that dormancy, and you can then it'll sprout uniformly. And so as we go through this, I just wanted to quickly touch on the basis for dormancy release and germination in small grains. Here you can see we have some heads that have a decent amount of green color on them. This is pretty much right at physiological maturity, right at the point of when those seeds are physically able to germinate. But there's these other factors like their abscisic acid sensitivity and a few other things like water availability, things like that that also determine it. But really at this point, they could germinate if conditions are correct. And so you start with really high abscisic acid sensitivity, no germination. As you move forward in the maturation process, you lose that green color, the abscisic acid sensitivity starts to go down, your seed starts to dry out. And then about harvest time, or just before when you would actually harvest, you enter after ripening. So the seeds start to become GA sensitive, gibberellic acid sensitive, They become sensitive to gas exchanges with the environment and start producing reactive oxygen species. And then that basically is what leads to germination. GA levels will rise within the seeds and trigger germination. And so we won't go really deep into this, but I wanted to touch on basically what was the majority of my work, which is the wheat pre-harvest sprout genes. And so we looked at what are called quantitative trait loci, and those are just areas of the genome that we've identified as being somehow associated with the trait. And so we've identified areas on most chromosomes in wheat that are associated with pre-harvest sprout. We don't necessarily know what genes they are or anything. We just know that this chunk might have 10,000 genes in it, somehow is related to this trait. That helps us because a breeder, even though we don't know the gene, we can still use that area as a way to breed to alter the trait because it's associated with the trait. So in some plants, that area will be associated with a susceptibility, and in some plants that will be associated with a resistance. So then a breeder can go right in, and just select for the resistant variety. And we can use genetic markers and things then to speed that process up. So we have these quantitative trait loci for pre-harvest sprout. Like I said, they've been found all across the genome, but there's 3 of them that have been found to have the most significance and have been validated across a lot of different studies. And this is how I kind of got started along this path. And so you have the 3AS QTL, which has explained a huge amount of the variation in pre-harvest sprout between wheat varieties, and this 4AL QTL that also explains a really large amount of variation. And so very recently, within the last few years, a few different scientists have dug really deep into these areas that have a lot of genes, and they've tried to identify the exact gene, that's causing these differences so we can understand the whole process. And so they've identified 3 genes that they think might be underlying these 3 QTL. Mother of flowering time, mitogen activated kinase 3, and viviparous 1. That's not really important, but my work basically went in and looked at these 3 genes very specifically in the plants and kind of confirmed or not that we were seeing that those genes affected pre-harvest sprout. And we did have some really good results with that we were able to pass on to the breeders that we'll be able to show here. We did the same thing in barley because we had a lot of success with wheat, so the Wheat and Barley Committee asked that we start pursuing this research in barley, basically. Excuse me, I'm gonna sub that twice. So we did pretty much an identical study in barley where we looked at the different QTL, then looked at the underlying genes and tried to analyze those genes correctly through sequencing and things like that. And not surprisingly, 2 of the 3 major genes were the same as the ones that we found. And so we had formed some overall research objectives, like really early in my PhD, that I've pretty much been addressing for like the last quite a few years. Not to assess pre-harvest sprout, susceptibility in small grains, commonly grown varieties, and also we test a lot of experimental varieties for the breeders. We wanted to assess the allelic contributions, and that's just the different versions of those genes that I was talking about. We wanted to assess the contribution of those different versions to the known impacts of PHS and common varieties, and see if we could find new versions of those genes that we could then use in our breeding processes. And then we wanted to integrate anything that we found, back into the breeding process to help make things more resistant, basically to pre-harvest sprout. And so for our plant materials, everything was generally field grown in triple replicate. We would collect heads, dry them and freeze them at physiological maturity. And in the case of barley, we actually did a lot more time points. I did it at physiological maturity, harvest maturity, and in after ripened grain. And so I said we'd talk a little more about physiological maturity, and how we were characterizing that in wheat was basically by this 75% loss of green color from the peduncle. And that was almost a little bit too early. So I probably honestly, for it went a little bit more, 80 or 85% loss of green color, because then we would actually get a little better test results. Anything before that, and your seed, not all the seeds are viable. And so it kind of skews the results of what you're testing there. And I actually found that more towards harvest seemed more relevant to the producer, because that was actually when the rains are hitting, when you're trying to get out there, and the things are actually a lot more susceptible. And so then with barley, it was actually even worse. And so we waited till there was almost 90% loss of the green color. And that was just because barley is really susceptible compared to wheat for sprouting and stuff. So, and the grains seem to mature quite differentially across the spike compared to the wheat. So we waited a little longer. So we collect them, dry them, freeze them, and we did test to make sure the freezing didn't impact any of our, our analysis. And I'd throw them into this misting chamber where I line them vertically like they would be in a field. Then they're misted every 10 seconds for 5 minutes. In the case of wheat, it was for 7 days. In the case of barley, it was for 5 days. And then I developed this little pre-harvest sprout scale here where 1 was no visible sprouting and 7 is completely sprouted with over 2-inch shoots and roots, basically. And you can see here that we actually had quite a bit of difference. You get some in there that have 0 sprout and some that are just, completely sprouted. And these were all harvested at physiological maturity. So I would go out every day for about 2 weeks and harvest them as they matured instead of harvesting them all. And so then in the case of the barley, I know I'm kind of jumping back and forth, but it'll just be more beneficial if we do that. We also used this thing called a weighted germination index. And so I said I collected heads at physiological maturity, harvest maturity, and then we did after ripened grain testing too. But the heads just fall apart at that point. So we actually just threshed the heads, and then we did a germination index, and that's just putting them in a petri dish and checking them for 7 days, and you basically weight the ones that germinate first. So it's just a nice way to basically complement the stock test. And then we performed our genetic analysis where the main genes of interest mentioned earlier for each small grain type were assessed for variation by directly sequencing the exons of the genes. And the exons are just the coding regions of the genes that actually are turned into protein and things like that. And so that's where you're most likely to find mutations that would actually make a difference to the trait that you're looking at. So this is probably the information that everybody would be the most interested in, and this is going to be like our varietal testing using those methods I just described. And so here you'll see I have them arranged by their sprout score, and if you remember, 1 was pretty much completely dormant, 7's completely sprouted. So you have like WB Quake, Decade, and Warhorse consistently. I know it has a 2 here, but I've actually tested it in a lot of other studies now, and it consistently comes in as my most dormant variety. I guess I haven't tested Decade as much, so it may be dormant also. But if you're looking at a good soft-eye resistant dormant variety, Warhorse is your go-getter there. And so I'll be actually continuing a lot of this as I'm starting at the station. I'm building a little bit of a different pre-harvest sprout analysis rig, so it'll be a little higher throughput. I want to start testing, our breeding trials, our variety trials basically every year. I'll put something up on the website so people can see how it was doing in relation to that year, because the temperatures actually make a huge, huge impact on this. So a lot of this data was collected 2016, 2017. I don't remember which year it was, maybe 2017. One of them was really, really hot and dry, and it caused a huge amount of dormancy in my varieties. My results were about 20% skewed towards non-germination. And so it was really interesting. And so I want to continue this over the years and try and, relate the weather patterns a little bit more to the sprouting. But the rankings are generally consistently the same across the years, even though it may shift a lot. And so then your most susceptible varieties I want to point out are some things like Yellowstone is mildly susceptible to sprout. Loma is a really popular variety, and it's actually pretty darn susceptible to sprout. It was one of our most susceptible. So just some things to point out, but if you have questions, we could always email me at the station or something. I'm going to continue this work, and I think people will be able to benefit from it. So people might not be as interested in this. This is kind of just looking at the different versions of those genes that we looked at. 3 genes. We found a susceptible and a resistant version for each, basically. And so here you can see they were called TAPHS1 for short, TAMKK3, and BP1B3. So when you're looking through your sheets here, you have the S for susceptible, R for resistant, then the number of lines that we tested that fell into each category. And so here you can see the pre-harvest sprout score for the ones that carry the susceptible version of this PHS1 gene generally sprouted like almost double in comparison to the resistant version. And we've actually found this across all of the different studies that we've done that wouldn't be included in this data. And then we found in a lot of the literature, this MKK3 and BP1 is actually more associated with sprout for some reason than this PHS1, but we don't see that in a lot of our northern Great Plains varieties. So we have forwarded this onto the breeder, and we've already been working on, breeding this resistant version of the gene into more lines so that we don't end up with great lines like Loma that are totally susceptible to something like sprout that could be easily avoided. Because we don't see any, and then we don't see any effects on yield. There's no differences in yield. We saw a difference in protein, but the resistant version had slightly higher protein, but that could have been slightly artifactual. It wasn't a huge difference. So then for that genetic analysis results, variation was detected in all 3 of those genes when we did the sequencing, but only the 1 gene was really strongly associated with sprout. And that was great because it gave us a quick, easy target for breeding. Start to integrate that into our lines. And so in wheat, there's actually 3 genomes. And so we actually only looked at 1 copy that was shown in literature to be associated with it, with sprout, but there's 2 other copies on the other 2 genomes called TAPHS1. You have 3A, 3B, and 3D. So we've been doing a lot of work looking at those other copies as well, and there's reason to believe that mutations in those lines are explaining what mutations in this gene wasn't explaining, kind of. So we have good targets anyway, I guess, to further increase these benefits, I would say. And so this is just looking at that TAPHS1 gene where you have the resistant allele versus the susceptible in the gray there. It's a sprout frequency as a number of lines. So the thing to take away is the resistant alleles kind of cluster towards the dormant side of the graph to show that generally those are the more resistant ones. So moving on to the spring wheat, which we've done way less work on than either winter wheat or barley. We just pretty much did this one single study. We found that like Thatcher, McNeil, Fortuna, Reader, those were all really resistant lines, whereas some of the more popular ones like Shoto, Declare, Rockford were a little less dormant. I feel like maybe some of this data for the spring wheat was a little bit of a fluke, so I'm excited to repeat it because some of our other studies have kind of shown that Egan was a bit more dormant than it showed up in this exact study. And that year was a little bit off with the harvest and stuff. So I think that the ranking of this could shift and probably be refined a little bit. The data wasn't amazing, if I remember correctly. We looked at those same genes in the spring wheat, and we found no variation in that major gene that we found in the winter wheat to be responsible for the differences we were seeing. Basically, all the spring wheats had the same version of that gene. And then they did have different versions of the MKK3 and BP1, but that seemed to not be associated with sprout at all. And so that was actually pretty surprising. That would tell us that there's something else going on there. And then lastly, we have the barley PHS here. We did this on that same scale. So here, you're just looking at the pre-harvest sprout score at physiological maturity and in after-ripened grain. We left out the harvest mature for the paper that we wrote for this. So I'm just showing, I guess, the data that we published. And so you can see that varieties like Stepford, Medallion, Steptoe, not sure if any of those were ever very common around here, but those are all really dormant lines. And then you can see here a lot of the most common lines, most of them AMBA-approved lines actually are extremely susceptible to sprout. And so with our barley, we actually grew quite a much larger study than we did with the spring wheat or the winter wheat. And so we had a lot of different end use types. We had malt, feed, and forage. And then out of the malt, we also separated the AMBA varieties because those are kind of like the newest and best varieties. And so we kind of were using that as a time capsule as old versus new almost. And you can see here that the newer varieties, the AMBA varieties, actually all cluster towards being moderately to extremely susceptible to sprout. We hypothesized that almost all malt would be really susceptible to sprout, because you'd think it was bred to be germinated. But actually, there's a ton that at physiological maturity, great amount of dormancy and a lot of really popular malt lines. So we found that to be really intriguing in that maybe there's different genes controlling this dormancy at different time points, right? And why can't we alter that at high dormancy at harvest that would rapidly decay in after ripening, because that would benefit producers the most. And so here is where you'll kind of see my physiological maturity sprout score. I included the harvest maturity germination index and the after ripen germination index. And basically what this shows you is the progression of this dormancy of a susceptible versus a resistant line. And here in the green is what we would call like kind of ideal lines, right? Conlin, which is somewhat has been a popular malting variety before around Montana, and Nepal, which is not so much. But at physiological maturity, those have really low sprout scores below 2 or at 2, which is totally acceptable. You wouldn't get dinged very much for that if you caught a little bit of rain late in the season, because these things were heavily soaked for 5 days. So if you can get those kind of scores in the field, you'd be great. And then especially Conlin at harvest maturity, boom, that dormancy decays very rapidly. But at harvest maturity, you still kind of want that dormancy of Nepal, right? Because if you get a rain now and you haven't got out there to harvest, you're still going to lose that crop. But then in the after ripen, that's when you want something like Voyager or any of these top varieties that has no dormancy, because then it's off to the malt house or replanting or whatever is going on with it. And so our idea is, to explore this different breeding schemes and try to get higher dormancy here in some of these quality varieties that haven't been that time. And so we looked at these 3 genes, MFT, MKK3, and a different one called ALA-AT. Found variation in all these genes. We found that 2 of these genes affect dormancy at different times in maturity, which is what we were hoping to see. One really affects dormancy at physiological maturity, and one really affects dormancy after ripening grain. So that gives, and they're not on the same chromosome, so we could easily breed and get a variety that would quickly have both of those genes in it, the resistant versions of those genes. And we actually found a previously unknown mutation in one of those genes. And so it's kind of exciting because now we're a source of germplasm for other breeding programs to get that into their varieties. And so kind of an overall summary, winter wheat varieties vary greatly for PHS. All small grain varieties do. Variety is really important choice if you have any problems with pre-harvest sprout. So there's a good mix of susceptible and resistant varieties all the way. Same thing for spring wheat. The genetics are much less clear than they were in winter wheat. For barley, the varieties also vary greatly, regardless of the end use type. A lot of the more popular AMBA malt lines are much more susceptible, something to keep in mind. We were able to find this novel mutation that negatively affects dormancy at physiological maturity. And this is all exciting because hopefully we can mix and match this stuff to benefit the people. Okay.
I have a question.
Sir.
Are the malt breeders, they care about dormancy?
No, they want no dormancy.
So, I mean, are you getting them to change that? Or are you just providing the information and saying, great?
No, I'm a big proponent, and I'm trying to, basically, it's kind of, all they hear from is the malt companies and what the end user wants. And it's the same thing with wheat, but nobody's willing to pay for that, right? And so who's going to lose in the end if there's no dormancy, and that's all they want is no dormancy? Well, it's the producer, because if they contract it and it gets rained on, I mean, you're just screwed out of your crop, right? Or if you're trying to take it to the elevator or whatever. So they aren't specifically concerned with that, but I have been bringing the point up more and more and more. And with this data, I think it starts to show them that it's possible to satisfy both parties almost, in my opinion. I think the next step is to start to analyze malt quality with the different versions of these genes that I'm looking at, because what happens if suddenly the resistant version actually has a crappy malt quality or something? Maybe this gene has dual purpose in the plant that we're not seeing yet. So there's definitely more research that we need to be done.
Have the malt companies and beer companies at the end, they've been doing some research over the years to find other varieties that do malt quickly?
Yeah, and that's the whole push for malt barley, because they lose money basically if it gets in the malt house and it doesn't uniformly germinate. Their recipes are so precise. I've actually been doing a lot of malt research and stuff. Before I got this job, I thought about starting a malt company. And if it doesn't uniformly germinate, your whole recipe is kind of thrown out the window, because all the grain will be at different stages of germination. Enzymes are all over the place, right? So they want everything to have zero dormancy and be completely at the same point. So, but yeah, I think that it's been that push for a long time, but I think that reading is just kind of difficult and it takes a lot of time and for somebody to just tackle the problem. So maybe I'll just spend some time in the greenhouse and keep working at it, and then we'll have a good variety that the other breeding programs, then they don't have to worry about it. Just take that, and run with it. So, any other questions? Okay. So we're going to kind of shift gears a little bit here. I just wanted to use this opportunity. Oh, I've been standing out of the screen the whole time. Sorry, guys. To talk about the Western Triangle, my new position up there, and what we've been doing. I know it's been kind of we've been almost down for a little while. We're kind of restaffing right now and stuff, but we have a lot of exciting things happening. The main thing that's been happening since I got there is just clean up. Kind of 20 years of stuff has accrued, and we're getting in there and just kind of out with 30-year-old documents and stuff, that's all digitized. I mean, there's just mountains and mountains of things that are just really old. So cleaning up a ton. Staffing's been the huge issue. We pretty much have me, an administrator, and a technician that's there sometimes, and the admin's part-time also. So we've been looking for a research associate and a farm ops manager. And recently, I think we finalized the research associate, and she'll be starting in May. And the farm ops manager, we have a good candidate interviewing on site tomorrow from North Dakota. So I'm really hoping that his interview goes well, because then I'm going to get him a job. So then also the next big thing is our greenhouse. We're getting the state-of-the-art research greenhouse put in right now. Swank's putting it up for us. It's actually way past this point. They have the whole head house on it. So basically this point back is a giant, going to be a giant heated head house. It's going to be a double bay heated, natural gas heated greenhouse so that we can continue our research efforts through the winter. We were slated to get like 4 or 5 of these across all the stations, but it's funny how all this works. They got the money for it, 5 or 8 years ago, and now when they go to spend it, they didn't account for inflation at all. So they gave us about $250,000 for each greenhouse. This thing cost almost $1 million now. So we were able to build 2 greenhouses. Luckily, our site got one because we've been so down, and I'm coming in new. They thought it would be a great thing to like boost the whole research of the station and stuff. So I'm thankful for that. And we're in a good situation to collaborate with Northern and Central also, because they're only 2 hours away on both sides. So it'll work out really well. And then Huntley is the other place that's getting one. So they'll actually make really good use of it too. But this is really going to transform the research we're able to do out there. And we're going to be doing a lot of breeding and some different cool stuff. And the next thing we're working on really heavily is equipment updating. There's no GPS out there. There hasn't been any. They have no idea where any soil samples have been taken. Like, just everything's falling apart. It's a freaking mess. So I've just been going through, upgrading things as I can. I'm trying to find cheap, cost-effective ways to upgrade things. And as I do this, I kind of find it to be exciting because I have the opportunity to experiment with a few different things. And then I can share that information with you folks. Like, I'm still experimenting with this, so I wouldn't run out and buy it, but I found this really great GPS system from this company called MLID. Centimeter, survey grade precision and things. It cost me $3,800 for a station and a rover setup and a deal for the tractor and everything. So I'm still getting all the kinks figured out. So I'll let you know if it's a crap shit, but we'll see. The next thing we're hitting really heavy is the variety trials. We got our winter wheat variety trials planted in this year, only on station though. We didn't have time to really get any off station. I came in right when planting was starting to happen. So it's just on station this season. Next year, we plan to do 5 to 8 off station. We're also looking for collaborators if anybody's interested for spring wheat and barley this year too. So for spring wheat, this year we're going to have 2 regular off-station nurseries of 25 varieties apiece, triple replicated, and then 1 acid soil off-station nursery. And then for barley, we're going to do the same thing, 2 regular off-stations and 1 acid soil. And those, I'm just letting the breeders choose their best varieties and things like that, the things that the producers are going to want to see out in the field. I'm trying to make sure it's consistent across those. For pulses, we're doing statewide variety trials with pea, lentil, chickpea, and we're doing some experiments with cowpeas as well. And then we're looking at doing some hemp variety trials. We were just part of a big $10 million grant push from the college to do fiber and grain hemp processing. It was looking at the economics and things like that of it. So we may get into that a little bit. Specifically, I'm developing my research program right now. There's a huge push by the USDA and our college to start getting into precision agriculture. And so I started doing a lot of investigation into remote sensing and UAV mapping and different data collection. And that's in conjunction with some of the other research stations. And we're trying to get kind of a standardized data collection thing going with these different new technologies so that we can make them actually really useful to producers. Because I know at this point, there's a lot of talk with UAVs and stuff, but nobody's seeing a huge benefit. But honestly, I think as the sensors are evolving and things are happening, I've been following this for quite a few years now, and it's coming to a point where I think it's going to be actually making a big difference for people. And so I want to throw myself at that. So we have things on station. I've been building small sensors that I can't find to measure temperature and soil temperatures and soil moisture from a distance can be transmitted for quite a few kilometers and last for years on tiny batteries and stuff like that. So you'd know, what the moisture is in one of your fields. It's quite a long distance, and you would know when you could take your tractor out there and start planting and things like that. We're working with this historical winter wheat nursery. It's comprised of the most popular varieties grown across the Great Plains in like the last 100 years, 64 different entries. We're going to be doing a ton of investigation on that. I plan to grow it for the foreseeable next 5 to 10 years. I think it's really interesting to see how the old varieties compare with new varieties. We may swap a few in and out of the newer varieties, but I'm going to keep all the old varieties the same. And then I'm going to use that as a jumping off point. And so are my colleagues for developing this drone data, because then it'll give us a nice set of varieties that would be quite different to collect all this data on. And then I'm going to continue my work on pre-harvest sprouting and seed dormancy, basically continue my PhD work, developing a high throughput assay system so that the breeders and everybody can send me a seed or heads at the right time, and I can just run it through the gauntlet and give ratings out, and then we can see how the environment's really affecting the pre-harvest sprout ratings. Another huge thing is the herbicide resistant kochia. I want to really try and tackle that. There's 2 of my colleagues that have recently come to MSU also, Dr. Lovery Shergill and Clint Byerman, are both weed scientists, are really interested in this too. And it kind of falls right in with the whole precision agriculture and gives us a goal to apply some of that technology to. And so there's already been some work that's pretty interesting done on this in 2018, where they were able to fly drones with hyperspectral cameras, and they could identify, I believe it was 5 out of 7 herbicide resistant kochias. You can kind of see here. The herbicide-resistant kochias have a different reflectance pattern if you measure it at the right wavelengths. And so they were able to tell and then accurately go and do that. 5 of 7, it's not 100%, but I mean, for one study, that's pretty great. And I'd like to take that and make it a little more extreme. So then the last major problem that I think I'm going to be really trying to at least collaborate heavily on, because I'm no entomologist, is the sawfly. We're working on a project right now aimed at parasitoid support. There's this little parasitoid that it's a little wasp that attacks the sawfly. And it really benefits from late blooming plants, like the cowpea, I guess, carries nectar really late into the season. And so we have this variety trial where we're going to grow a lot of late blooming things and measure different sawfly parameters, and then it's going to do all that stuff. I just got to grow plants, so we'll have some data on that eventually, but it's going to be a pretty exciting study, and it would be pretty cool to be able to, basically rear these little tiny wasps on the edges of your field and have your sawfly numbers go down quite a bit. And then the last, I guess, is the hemp potential, because we've been just pushing. We just did this huge grant. I've had a lot of meetings with, there's a few companies in Montana. We have IND Hemp and American Harvest. And so I really see CBD as just kind of gave hemp this really bad name, kind of left a lot of sour taste in people's mouth, but there's these companies pursuing hemp for fiber and grain and other things, and they actually have processing facility in Fort Benton now. IND Hemp has a really large grain processing facility down there. They are building a fiber processing plant right now. When I was down there a couple of months ago, they already had the cement board and everything, and they're already planning a 5-time scale up of cold facilities. And so eventually, right now, they only have about 10,000 acres that they're contracting out, but eventually they said they would like to be at the point where people can, they're not contracting anymore, it'll just be bring it in. And so Fort Benton's pretty centrally located. So I think I want to do some work looking at the varieties and possibly a little breeding, because there's a lot of room for improvement from what they're working with right now. And for organic hemp grain, I think they said they were paying $1.25 a pound. And for non-organic, it was 55 cents. So, it was pretty decent, and it's something we could work into the rotation that would be different than so we'll be doing a little experimenting with that. And then just to be on the bandwagon, there's all sorts of uses for it. Yeah, so we won't go there, but yeah, that's pretty much what I had today. I'd love to talk with y'all about anything. Feel free to reach out at the research station. And really, I want to know what your problems are, because that's all I really care to work on. I haven't had many people approach me and say, I have issues with this or that. And So I just kind of picked the things I saw as were the major issues on paper, right? And that's what we're trying to tackle now. So I'm open to any kind of other research ideas for sure.